My name is Timur. Thank you all for coming and for having me here. It's really cool. I'm going to talk about C++20. I don't have any jokes on my slides, unfortunately. I don't do jokes, so I'm sorry. And yeah, so what I do have, though, is I always have a astrophysics kind of picture on my first slide. So in this case, this is the... Does anyone know what that is?
Space.
That's something you actually see with the naked eye on the sky. Maybe not here, but... Sorry? It's the Pleiades. It's like an open star cluster. You can see it. It's kind of like a blurry kind of thing in the Orion constellation. So this is an open cluster of like hot young stars that have just formed and started shining. And this is kind of what we're going to be talking about, kind of the C++20 features, like the many little small C++20 features that have just formed in the form of actually now being in the C++20 committee draft. And that you will hopefully all be able to use soon. So I have been on the committee for a few years now. There's something in the way, right? And this is where we are kind of right now in the release cycle for C++20. So we just had a committee meeting just a couple of weeks ago in Cologne. And at the end of that meeting, we shipped what we call the committee draft, which is kind of the release candidates, essentially. So now we know what the feature set is like. We now have 2 more meetings to fix any bugs that come up at last minute, basically, and then we're going to ship the new international standard for C++20. So I gave like a draft version of this talk before Cologne at St. Petersburg. And since then, some stuff has changed because we actually removed some of those features. So I had to change some of my slides, and some of the kind of really cool stuff that people were asking most questions about actually didn't make it. So... so yeah, anyway. So what you're going to be talking about today is, so this is more or less C++, right? So it's about 1/3 of the standard is actually the language itself, and about 2/3 of the standard is actually the standard library. So we're not going to talk about anything in the standard library. We're only going to talk about the language. And now C++20 comes with a few pretty big new language features. Which are concepts, modules, coroutines, and consistent comparison, or the Spaceship Operator. Contracts actually is also something that got removed in Cologne. I'm not going to talk about this here. If you want, you can ask me at the pub later. I can tell you many interesting stories about that. But anyway, so these are kind of the big features, right? So concepts, modules, coroutines, and consistent comparison are all kind of relatively big features. We're not going to talk about any of those either. So we're only going to talk about all the other little kind of remaining bits that you might not kind of stumble upon immediately when you look at, C++20, but they're there and they're really useful. And yeah, so these are kind of the broad areas that we're going to cover is initialization, which is what we're going to start with. Structure bindings, we're going to talk about lambdas and functions. We're going to talk about templates, some constexpr stuff, and then a few miscellaneous bits in the end. So first topic is initialization. Maybe some of you have seen my talk about initialization, which I gave a short while ago. So I'm just going to basically start off where I left at that particular talk, which was at the end where I was talking about C++20 initialization. So we're going to start right there. Most of the kind of changes in initialization C++20 have to do with aggregates. Aggregates, I think, are not actually quite as useful as some people think, but they are useful sometimes, and they have been given a lot of love in C++20. So in particular, what is an aggregate? This is an aggregate, right? So it's a thing that has a bunch of members, and you can aggregate initialize it. Doesn't have to have any constructors or anything. So what we did in C++20 is we redefined what an aggregate is. So this is actually the change. So in C++20, as soon as you have a declared constructor, it's not an aggregate anymore. And that is looks like a tiny change, but it's actually breaking change, and it has been not very easy to get this through the committee. But what this does is it fixes like a kind of annoying thing. So in C++ 17 and before, you had this thing where basically you could have a struct which defines a bunch of members, and then you delete the default constructor. And whenever you do that, most of the time what that means is that whoever writes this class, they don't want the user to be able to initialize this class, right? This is why you would delete the default constructor. You say, don't instantiate this. You shouldn't be able to create one of those. So what happens is, well, if you do the W1 here, yeah, you get the error like, default constructor is deleted. You can't do that. But it turns out that using aggregate initialization, you can circumvent it by just adding brace. Now that's no longer trying to call the default constructor anymore. Now that's doing aggregate initialization, which does something completely different, right? It just initializes member-wise the thing without trying to even call any constructors. So just by adding brace, you could kind of circumvent the declared constructor and initialize this thing anyway, which is not what you want. So that has confused a lot of people. So now we say, so basically the reason why that was the case is that in C++17, if you go back, an aggregate can have no user provided constructor, but if you say equals default or equals delete, it means you don't provide it, but you define it. You declare it, sorry. You declare it, you don't provide it. So now we say if you declare it, it's already not an aggregate anymore. So in C++20, as soon as you have anything that looks like a constructor declaration, it's not an aggregate anymore, so you don't have that problem. So I think it's kind of clean because now aggregate initialization can never get in the way of like calling a constructor, so it's actually more reasonable. But it's actually breaking change, so it was yeah, interesting to advocate for this particular change. But yeah, anyway, so another thing that we have in C++20 is we actually have a new way of initializing things, which is called designated initializers. Those of you who write C might know this. This is a C99 feature. So in C had it since C99. So again, aggregate initialization. So how aggregate initialization normally works is that you basically write the initializer list, and you can omit things at the end, and then they're going to be initialized with 0, right? So you don't have to spell out all the initializers for every aggregate element. You can omit some at the end, and then they're going to be just kind of 0 initialized. So what you can do here is you can write the individual members with this dot member name syntax, and then you can omit some in the middle as well. So here you would initialize A with 3, and C with 7, and B would be initialized with 0. So this is this interesting property. Why aggregate initialization is actually really cool is that if you use it, you can never end up with uninitialized members, and this is the case here as well. So again, this is essentially a C compatibility feature, but there are a few differences between the way it works in C and the way it will work in C++20. So in C, you can do this out of order, so you can initialize C first and then A. In C++20, you cannot do that. So you can't you can omit things in the middle and the beginning and the end, but you can't flip the order. And the reason is that in C++, unlike C, we have constructors and destructors, right? And you, like if you have members, you kind of construct them in order of declaration and you destruct them in the reverse order. So order kind of matters. So which is why you can't do it out of order. You can't nest them like here. But that's fine because instead of writing .c.e, you can write .cbrace.ebrace, and that's going to work. You can't mix designated initializers with regular initializers because why would you ever want to do that? I don't know. And then you can't do it with array. Like apparently in C99 you can say dot square bracket index, which again I don't know why would I mean that wouldn't pass my code review anyway. But so anyway, so in C++ you can't do that. But apart from these limitations, it works the same as in C, and it's a useful, cool new way to do aggregate initialization. Another kind of minor fix that we have is there was this other annoying thing where if you have uniform initialization, basically initialization with braces, you could do it in a regular declaration, you could do it in a new expression if you do something equals new something. But then there was this one annoying thing where they wouldn't behave exactly the same, where a brace initializer wouldn't be able to deduce the size of an array, which is not something you would ever write. I think this is not really real-world code or anything, but it was like an annoying inconsistency because you had to teach, okay, if you use braces for initializer, they have this weird thing where in new expressions they behave differently. And the reason is that simply the committee in for C++11, when they introduced this new brace initialization, they just forgot this case. So, so now we fixed it. One other thing about aggregate initialization, again, aggregate initialization got a lot of love in C++20 is, so we fixed a few problems in an interesting way. So there was one problem with brace initialization that you can't put it in a macro, right? So if you have widget paren 2, 3 paren, there is a special rule if you pass a macro that it realizes that these are kind of like constructor arguments or something. But if you write braces instead, again, there was no special rule like this added, so the preprocessor doesn't know about braces. So what it would do is it would look at this widget brace 2 comma, and then at that comma it would think that the first macro argument has ended, and the next thing is the next macro argument. And at that point, you have like an open brace, and everything's just kind of completely broken, and your parser is just going to explode. Sorry, the preprocessor, not the parser. And the other problem with braces is that you can't really use them in templates, right? So you can't write an in place or a make unique that works for aggregates because you can't perfect forward a brace init list. So the fix for this is this paper, which basically allows you to do aggregate initialization with parens, right? So this now in C++20 will compile. And this works with all aggregates, including arrays. So you can even initialize an array like this, right? So it looks a bit unusual at first, but actually, if you think about it a bit more, it's actually beautiful, I think, because parens and curlies pretty much mean almost the same thing now. So I think, you know, when we had like uniform initialization in C++11, there's a few problems with it, but this is kind of, I think, this is like uniform initialization 2.0, right? So this is actual uniform initialization. So you can write either parens or curlies, and they will pretty much do the same thing, except the parens will not call a std initializer list constructor. So which is really cool, because then the recommendation kind of becomes use the curlies if you want to tell the reader, yes, I want to call a std initializer list constructor here, right? So you can kind of disambiguate these weird, in the other talk I had like these examples where you have like vector with like 2 numbers, and depending on whether you use curlies or parens, a different constructor gets called, and it's like really weird. So here you can say curlies mean I want to call initializer list constructor. And the other thing that they do is you get an error if you have narrowing conversions inside curlies, so that's also the same here. So parens do not care about narrowing conversions. But otherwise, they do the same thing. So last thing, which has to do with initialization, has to do with static initialization. So here we have a static variable. Does anyone see a problem here? So you have a kind of color. This is something that happened to me in a kind of real world project. So you have a static variable red. Obviously because it's static, you have to initialize it in a CPP file, which is fine. But the problem is if you then have another static object that uses the color red, right? Because this is what we call the initialization order fiasco. It means if you have static objects in different translation units, it's kind of not defined at which point they are initialized or in which order they are initialized. So if you have a static color that you initialize in one CPP file, and you have another static object that depends on that object in another CPP file, that will probably crash, because at that point it's undefined which one will be initialized first. So you can get around this, in C++11 even, by giving it a constexpr constructor, and that means it becomes a literal type. We're going to talk about this later as well. It means that basically literal type means you can instantiate it at compile time. There is a way to construct it at compile time. So then, if you have one of these and you have like a static object and it has a constexpr constructor, then constant initialization kicks in, right? And it says that because you can initialize it at compile time, it's guaranteed to be initialized before it even starts initializing the kind of non-constexpr ones. So at compile time it's definitely going to be initialized. You're not going to run into this problem. The problem here, though, is that because it's constexpr, it might be executed at compile time, so you might get constant initialization. In this case, you do, because you just have literals there. But if they are not known at compile time, then you might have this thing at runtime. So, for example, if you do this, is this going to be instantiated at compile time? You don't really know. It depends on whether this function is constexpr, right? And so on and so on. So it's not really kind of obvious. So this will also compile, but the second one, but it might then again get you in the situation where it might be undefined if you want to use it for another static object. So what you then really want to do is to fix this is there's another thing you can do is you can say, well, make the object itself constexpr, right? And at that point, you're again guaranteed that basically it's going to be constant initialized at compile time. You're not going to run into this problem. And if you try to do something on the right-hand side that isn't compile time, that you're going to get a compiler error. So that's, again, safe. But the problem with constexpr is that it forces it to be const, right? What if you don't want this thing to be const? What if you want this to be an object, which is like a static object, which you want to be initialized when you use it, but it might change its value later. You don't want it to be const. And for that, we don't have a solution in CSS 17. Right, so and then we're going to be back in this situation where we have to remove the constexpr because otherwise you can't modify it. Well, in CSS 20 we have a new keyword which is called const init. So we have lots of new keywords that start with const. It's really great. I'm going to have another one later. But this is const init. And the const init basically says this is not necessarily const, but it needs to be initialized at compile time. So this is kind of like enforces the kind of constexpr bit, but without the const. So then what happens is, okay, that was confusing. So what happens here is that const init says you have to initialize it at compile time. So the thing at the right has to be an expression, a constexpr expression. So you can never run into this order initialization fiasco, but it's not const, so you can still modify it later. But the guarantee it gives you is that it will always be initialized before your program runs, which is great. And another, okay, I have one more initialization related thing, which is range space forward initializer. So we already have basically if with initializer and switch with initializer in CSS 17, right? So now we're going to get range space forward initializer as well. Why is that good? Can someone spot a problem with this particular code here? Chris? Yeah, so the first one is returning a PR value, right? The database is being returned by value. So get database returns a temporary.
If register user stores user somewhere, then it's going to be a dangling reference.
Yeah, exactly. So that might be UB because the autoref is going to extend the lifetime of a temporary, but if get users actually is a reference into the database itself will go out of scope. Right? By the time, like after this red thing has been evaluated, database goes out of scope, poof, and then get users as dangling, and then you get undefined behavior. So how do you fix this in CSS 17? Okay, well, you have to do this first, which is fine, but then you're going to leak the database into the outer scope, which you don't want to do, so you need to surround it by braces as well, which is not nice. So in CSS 20, you can just do this, which is nice. So if works like this, switch works like this. Obviously, the normal for has this as well, and now the range space for has this too. So yeah, this is cool, I think. Yeah, we're done with initialization. What do we have? We have structured bindings. It's another great feature. So structured bindings. Everyone here knows about structured bindings? So basically what happens here is you have something that consists of parts. Like in this case, you have a struct with two members. You can have an array. You can have a tuple. Anything that kind of consists of several parts. And then if you want to initialize a variable of that type, instead of giving a name for the whole thing, you can give a name for its parts. And then you have this kind of square bracket syntax, and then basically A and B are going to refer to, so getWidget will return a widget, which is going to be the whole object, but you're not giving a name to this object. Instead, you're binding A to the member I and B to the member B, and then you can use them later. So this is a CSS 17 feature, but it was kind of limited in CSS 17. So in CSS 20, you can just do a little bit more with this. Because essentially, you're declaring a variable here, right? Except that you're not naming it, you're naming the parts of it. But you're essentially declaring an object here. So in CSS 20, so in CSS 17, it couldn't be static, it couldn't be thread local. In CSS 20, it can be all these things. And another thing is that you can now capture structured bindings and a lambda as well, which in CSS 17 doesn't work. CSS 17 says, well, A does not name a variable, so I can't capture it in a lambda, which makes sense because it's not a variable. That's kind of the really important thing to understand about structured bindings is that they're not variables. They're names for parts of another object, which is the actual variable, except it doesn't have a name. But this doesn't work, which is, unfortunate. So in CSS 20, it does work. There was quite an interesting discussion on the committee about what this is actually supposed to do. So does it copy? So okay, so we capture a by value, right? So obviously this function will work and everything will be fine. But is it going to copy? Because if you capture by value, it's going to copy something, right? At least notionally. Is it going to copy the whole object, this kind of unnamed whole thing, or is it going to copy only the member? Which one do you think it should do? So it copies just the thing that you capture, which is kind of reasonable, right? So if you want to capture an int, you're going to be copying an int. So speaking about lambdas, let's speak a bit more about lambdas, because lambdas also got a lot more interesting on C++20. So, okay, so first of all, lambdas inside a class. Here's a lambda inside a member function of a class. Is this going to compile? Pop quiz time. Nope. No, what's the error? It's not capturing this. Okay. So what you want to do is, in order for this to make this work, you need to capture this, right? And that's fine. Now, so what does this do exactly? Is this going to capture, because this looks like there's like, remember like before we had this capture with the A, right? So it captures it by value, it copies it. So here, it's not actually capturing this, so it's not capturing the object by value, right? It's capturing this pointer by value, which means it captures the object kind of by reference, right? It captures the pointer to it. So this is confusing. So what then you want to do if you want to tell the compiler, no, please capture this by value, you have to then write it like that, right? And that will actually capture the thing by value. Here's the tweet. So someone wrote that every time I type the characters star this. Yes, this is, I think, a bit unfair, because this whole syntax kind of is you know, the fact that this is a pointer is because by the time Bjarne came up with this, there were no references yet. References were introduced much later, right? So this is kind of a historical artifact, which at that point which was even way before like C++ was standardized, we got references. But at that point, it was kind of too late to make this a reference. It would have been already then too much of a breaking change. So we're left with the situation where we are. But yeah, so what you then could do is you can do it like this. So imagine you would, basically you want to, what you want to do is if you want to capture basically the A by value, right? But then this, you might want to capture by value or by reference, right? So if you write it like that, it's going to capture A by value and then the object by reference, essentially, right? It's going to capture this pointer by value. But it's really confusing. So you want to say, no, I want to capture everything by value. Or you want to say, so then you would write equals comma star this, or you want to say, well, no, I mean this. You know, capture, you know, A by value and capture this with the usual pointer thing, which is what this does. But you want to make it explicit, right? So you want to write this, right? But you can't, because it's going to say, well, you're already capturing everything by value. You can't specify that you capture something specifically by value as well. And so in C++20, that's going to be valid. So that was kind of a very long explanation why this is a good thing to do and why it's a good thing that this is now, because it's documenting what you're doing, right? Right, so what else you can do in CSS20 with captures? You can capture a pack. You can expand the pack in a capture init. So you could capture a pack before, but now you can expand it in a init capture, which is cool because you kind of can perfect forward initialize things into a Lambda, which is really useful if you're doing kind of generic stuff. So this is, I think, more of an exotic feature, maybe if you don't write like generic code a lot, but there's more. So these are kind of the two really big ones in my opinion. So now you can write lambdas in unevaluated context, and you can they're default constructible. and default assignable as well, as far as I remember. So that's really cool because then you can do this, which you couldn't do before, right? So you can write a lambda and then use that in an unevaluated context like size of or decal type or things like that. So then this is going to give you the type of this lambda which you wrote right there. And the fact that they're now default constructible means that now you can declare a lambda like this, which, you know, no one would use this, right? So you would write auto f equals brace, bracket, bracket, brace, brace. But you can't use auto for members. So what this allows you to do is you can have a lambda as a member of a class, which was impossible before. Now it's possible. So, okay, still, like, this is playing around with things that you wouldn't want to ever use. But actually, this is really useful. So just when Corentin and me were on the train from London to Edinburgh earlier today, we found a few very interesting use cases for this. So one of them that Corentin mentioned was if you have a unique pointer with a custom deleter, you can just declare your own kind of custom type with your own custom deleter, and you can just write the lambda inside the template argument list, just like this. So decal type and then the lambda, that's going to be your custom deleter, and then that's just going to be the type of that deleter, and that's going to be the type of your pointer. Another one which I find kind of useful is set and map and these things which take predicates as template arguments. You can just write a lambda just right there in the template argument list as well. So this is how you're going to compare your widgets, and this is going to be your set type. There's a question?
Just a quick question. Are default constructed lambdas aggregates?
Default constructed lambdas aggregates? No, they're not. But why would they be?
So let's just think if you had a lambda with certain captures, but then if you just call the type of it and then declare it somewhere else, you need to initialize it for its members?
No, you can't really do that.
I was just wondering if that was possible.
No. But now I want to know why you want this. So let's talk about this later. So yeah, it gets more interesting. So okay, so you can use them in these unevaluated contexts. You can default construct them. Okay, fine. So they're becoming more like objects. But actually, the other thing, so we have since C++ 14, we had these generic lambdas, right? Where if you have a parameter, the lambda takes parameters, and you put an auto in there, then it's actually like a template. So now the cool thing is, so we have concepts in C++ 20, which I'm not going to talk about, but as a side effect of having concepts, we now have also generic functions, which means that you can use the same syntax for just any function. You can write an auto parameter, and then that function is essentially going to be a template, right? So this is equivalent to template typename t auto f t a, essentially, right? So the thing that lambdas could already do since 14, now functions can do as well. And so the other thing that you can do with lambdas now, so again, so you have, so these are both templates, right? Lambda template and function template. Now, if you want to specify the template, for example, you need the template typename t, like you want to do something with the t. So for the function case, you could always just specify you could use kind of the long syntax, right? Template typename t, and then you have the t in there, and you can do this. So this, for lambdas, is not possible in C++ 17. In C++ 20, you can define now also the template parameters for a lambda, right? So you can do this, and then you can have the t in the lambda, for example, if you have a dependent type in there. Yes?
Hey, sorry, going back a little bit quick to the lambdas in unevaluated contexts. I know there's discussion on restrictions of where you could put them because you don't want to end up having to mangle a lambda or something. Do you know where those restrictions ended up?
So the question was, what are the restrictions on doing this unevaluated context lambda thing, because you could run into problems with mangling them?
Yeah.
I mean, it's just like a compiler-generated type name, but the compiler knows about it. So why don't you?
Discussions about places you could not put these things because it would cause issues.
I'm not aware of that. It might have been a discussion that I was just not part of.
Sure.
I'm not aware of these limitations, but let's look it up. Maybe I missed something. But as far as I'm aware, Oh, so something I should mention. This only works for lambdas that don't capture anything, right? So sorry, the decal type thing would work like this, but the default constructor, you can't default construct a lambda that captures anything, because there you have essentially members that you would have to initialize, but the thing that you're capturing. So you can't have a default constructor because it takes parameters. So this only works for lambdas that don't capture things. So because obviously if you, this thing, even if you can put it in a decal type, the moment you construct the set, you would have to default construct the lambda, and that wouldn't work. So, but I don't think this is what you mean. I think there was something kind of more complicated compiler technical stuff, which, yeah, I don't know. Let's look it up later. Maybe there was something. Right, so we had generic lambdas, now we have generic functions. We had template argument lists for functions, now we have them for lambdas. I think now the only thing that we're really missing is to have kind of this shorter syntax for regular functions, which is something that maybe we're going to be writing a paper about. Okay, so we're talking about templates already, so let's keep talking about templates. So templates, non-type template parameters. So what are the things you can put in there? Like you can have ints, for example, as non-type template parameters or bools, like these kinds of fundamental types. You can't have something like this, right? So this actually compiles, I think, but then as soon as you start to create one of those, you get a compiler error. It says, well, chrono duration is not a fundamental type, or you can't use it as a non-type template parameter, which is kind of not good because essentially it's just wraps an int, right? So these durations are just kind of counters inside. So they're just like kind of strong types around like an integer or something like that. So there's no reason, like if you compile it down, in the end, it's just going to be an integer. So there's no reason why you wouldn't be able to use them as a non-type template parameter. And it's completely reasonable, I think, to want to be able to template on something like that, right? But you can't, because in C++17, a non-type template parameter can only be basically a built-in type, pointer, or like a reference, and that's it. So in C++20, we changed the rules, and now you can do this stuff. So these are the new rules. Anything that is a literal type that has strong structural equality can be a non-type template parameter. Okay? So the literal type bit we talked about already. This is essentially an object that you can construct at compile time, right? That has a constexpr constructor. And obviously like ints and these kinds of things are also constructible at compile time. But what is this strong structural equality thing? So basically it's this kind of condition where if two values of this type compare equals, and then you use them as a non-type template parameter for some templated type, those are going to be the same types. And this is a really important property if you're working with templates as far as the compiler is concerned, because what the compiler has to do very often if it compiles your templated code is it has to check whether two types are the same, right? So you have template something, and then there's going to be some kind of template parameter inside, and the compiler has to see, is this the same value as the other value that I already have a specialization for example? And is this whole thing then going to be the same type? And these kind of checks whether something is the same type are really important. So you need to be able to do that. And if you can't do that, then you can't really have something as a non-type template parameter. But if this property is fulfilled, then there is a way to make it work in C++20 now. And now I have to talk a little bit more about how does it actually work. And for that, we need to talk a little bit about the spaceship operator, which is the three-way comparison operator, which I'm not going to talk about, except so we kind of need it here. So this is kind of the thing that makes it possible. So imagine you have something that just has two integers inside, right? So you have like 2 points and you want to compare whether they're the same points. This is trivial, right? You say, well, 2 points are the same if x is the same and y is the same, right? So, but what you have to do if you want to make this compile is you have to implement like 6 operators: smaller, greater, smaller than equals, like greater equals, equals, unequals, and probably like you know, like const versions of them or something. I don't know, like you're going to end up writing a lot of boilerplate. Oh, they're all const, but yeah, anyway, so you're going to have to write at least 6 operators. So in C++20, you can kind of let the compiler generate those by saying, so there is this kind of operator spaceship, which is the thing that lets you define just like basically one operator, and it's going to generate the other 6. And then you can default it, and then it's going to say, okay, don't even declare it, sorry, don't even define it, but you know, just do the thing, like basically do member-wise comparison. And if you write this line, then it's going to just generate member-wise comparison for your type. And then that's going to compile. And then actually, if that's if that has this property that we discussed, that it's strong structural equality, then the compiler now can say, oh, okay, so now I know how to compare these things for equality. So now I can do it at compile time, right? Because this is a literal type. And now you can use them as non-type template parameters. Yes, there's a question.
Less than defined as this type.
Sorry, can you repeat the question?
The default sort of less than this type.
Oh, it would do like lexicographical compare. So it would compare the first members, and then if they're equal, it would compare the second members. So it's called a lexicographical compare. That's kind of what you want. If you want something else, like for example, if you compare like a vector, that's probably not the most efficient thing if you want to do this member-wise, because you can in the beginning, just compare whether the sizes are the same, and if they're not, then you can just omit the rest. And in this case, like it's more efficient than doing the naive lexicographical compare, but then you would have to write it yourself, basically. Yes?
You can just use equal. You don't have to actually use spaceship, right? You can just default the equal operator.
Yes, you can default the equal operator, and that's enough for this.
Yeah.
If you do this instead, you get all the 6 for free.
Yeah.
So that's kind of better, because then also they're going to have all 6 and they're all going to be right and they're all going to be consistent. But yes, just to have this, you can just delete default equals. All right, cool. So if you do all this, then this works. And this is great because you can do lots of cool stuff with it. So some questions you might have now. Can I now use float and double as non-type template parameters? Because that keeps coming up all the time. No, you can't, because they don't have strong equality, right? Because there's no strong order really on floats, like 0 and -0 compare equals, and how do you compare nons? There is a way to define a strong order if you have like IEEE floats. It's defined in this kind of weird way that kind of works. And there was a proposal actually to say, okay, we're going to use that to then be able to use floats as non-type template parameters. That came up like at the last second in Cologne, and people were like, whoa, no, like this is like too late. We're not going to do this now. So this is not going to happen. The next thing everyone asks is like, can I now use strings as non-type template parameters? Because this is what you really want. This is really cool. This is like, for example, for reflection and things like that, right? Where you can actually get like the name of a type as a string. And then you want to use that string and template on it and do other cool template metaprogramming things on it. So, well, in principle, yeah, you can do this. But actually, it doesn't work with std string. So what you would have to do is you have to write your own fixed string thing that does have the defaulted spaceship operator. And then you could use that string type in this way. Except that we didn't add that to the standard library, so you kind of have to do that yourself. Yes, Chris, question.
Why doesn't it work with std string?
What? Sorry, what?
Why doesn't it work with std string?
Because std string doesn't have a defaulted spaceship operator.
But
Yes.
it has a default equal 1. I mean, it has an equal 1, and the string is constexpr, so I think it should work.
Okay, there is a reason why it doesn't, but I'm not sure now. Let's talk about it later.
Essentially what Corinne was asking is why I got confused, but I'm happy to take that.
Okay, I don't know this off the top of my head. Let's figure it out later, okay? How much time do I have left?
So you've been talking for 39 minutes and 30 seconds.
Oh, so we're good. Okay, cool. So we can talk about CTAD, which stands for Class Template Argument Deduction, which is, everyone has not heard about CTAD? Who has heard about CTAD? Okay, so CTAD, I should have really have a slide like explaining CTAD. It's like a C++17 feature. Basically what you can do now is you can write std vector v equals 1 to 3. You don't have to write vector int. If you just write a vector v equals brace and then a bunch of integers, it's going to deduce that it's a vector of int. Right? So you can omit the parameter, the template parameters, and it's going to deduce the template parameters from the initializer. Which has been around since C++17, which is cool because, like, for example, these things get quite long. Like, for example, sometimes you have to write things like std, I don't know, std unique lock, std recursive shared mutex, and then you can just omit the recursive shared mutex bit. Because that's the thing that you're going to give it as an initializer, so it can just deduce that. Yeah, sorry I don't have a slide about this because it's a C++17 feature. But what we got in C++20 is we plugged a few holes. So now you can do class template argument deduction on aggregates and on alias templates. So basically, if you have this kind of thing where you have a templated kind of aggregate, for example, and then you have basically a T and a U member there, and if you want to initialize it like with an int and a bool, for example, you want to deduce that it's an aggregate pair of an int and a bool, right? Obviously. So for std pair, for example, that already works. You can write std pair p equals 1 true, and it's going to deduce pair int bool. But for an aggregate, it doesn't work because the way the rules work in C++17 is it looks at the constructors and then it deduces that from the constructors. An aggregate type doesn't have any constructors, so that's just not going to work. So in C++17, you always have to write this explicit deduction guide, which is this next thing there in the middle with the weird kind of arrow, which is like an explicit thing you have to write to tell it, okay, and whenever you see an aggregate pair being constructed from a T and a U, deduce an aggregate pair of T and U, which is kind of boilerplatey and not necessary. And so in C++20, we just generate that for you. You don't have to write that anymore. It's just going to, this is going to compile on the right-hand side, and this is kind of what you want to write. So yes, there is this kind of interesting algorithm that figures out what the template parameters actually are, but you don't have to worry about it. And the same for alias templates. Like, for example, for a vector, it works, right? So you can write vector v123, and it's going to deduce vector in. But if you have an alias template, like, for example, PMR vector is an alias template of a vector with a specific, like, polymorphic allocator. And that's not going to work in C++17 because CTAD doesn't look into alias template. So if it has an alias template, it just says, yeah, I can't do CTAD on that. So in C++20, we fixed that. So it now also works in alias templates. So yeah, you can do this. You can write PMR vector, and it's going to deduce for you that it's a PMR vector of int. Am I going like too fast or too slow? I don't know. So I should have said this in the beginning. You can interrupt me at any time with questions, but you have already been doing that, so you're doing well. Thank you. Keep doing that. Right. So constexpr. So we have a lot of features in C++20 which have to do with being able to do more things at constexpr at compile time. And I can't really go through all of these new features because this is like a whole talk in itself. But luckily I don't have to, because two people who know a lot more about this than I do and who actually have been deeply involved in developing these features have given these talks already. So this is what I recommend you do. So a lot of people have worked on the constexpr stuff that I'm going to quickly mention now. But those two people in particular, I think, had like a big contribution, and also they gave these talks. So David gave a keynote at C++ Now just a couple of months ago, and then Louis had this talk at last CPPCon, and they both kind of go through all the nice things you can now do at compile time. So both of these talks, highly recommended. There's like obviously other people who have worked on this stuff. So there's Andrew Sutton, Richard Smith, Peter Dimov, and other people. But you know, really, like if you watch these talks, then I recommend you do that. It's pretty interesting stuff. So here I can just offer this kind of short list. So in C++20, if you have a constexpr function, now you can have a try block in there. So you can't actually throw an exception, but you can have a try block in there. You can have an assembly code block in there as well now, as long as you don't actually evaluate it at compile time, because that doesn't mean anything. You can use a union at compile time, which is great because then you can use it to implement a compile time variant. You can call virtual functions at compile time, right? So as long as your virtual class hierarchy is something that the compiler sees, and it can figure out in compile time what the actual class of this thing is, it's going to let you call virtual functions and do this kind of thing. So now that you have kind of constexpr polymorphic classes, you can also use dynamic cast and type ID. And the big thing is you can now use new and delete at compile time as well. So it's not going to actually allocate like memory at runtime or anything, but it's going to like, but it lets you use kind of dynamically defined kind of amounts of memory at compile time to generate compile time objects. And what this is really useful for is to implement std vector and std string constexpr. So std vector and std string, this is library stuff. I'm not going to talk about library stuff, but std vector and std string are constexpr in C++20. Yay! So you can use them for compile time programming, right? So you can have a collection of something at compile time, like a collection that can grow at compile time. That's really cool. Like again, if you want to, this is all kind of setting up the stage for like reflection in C++23. But these are, really interesting features already today. So really, I think there's not that many things left that you can't do in a constexpr function. So you can still not have a goto in there. You cannot do a reinterpret cast in there, and you cannot throw an exception in there, which basically means like the constexpr thing is like the sane subset of C++. So C++ without the things you shouldn't be doing. So, and the other nice thing actually about constexpr is that there's no such thing as UB, right? Because like if you have a constexpr function, the result of that might be used to instantiate a template or something like that, right? So the compiler has to figure out, every time you have something that doesn't work, it can't just say it's UB, because at the end it has to create a type from that or something like that, right? So it's going to track everything you do, and whenever something would be UB at runtime, but you do it in a constexpr context, the compiler will give you a hard compiler error. So actually, if you then stick constexpr on all your functions, you're gonna, like, your compiler is gonna detect all your UB for you for free. It's really cool. And then there is, so there's really this other feature which is interesting. So about running code at compile time. Like for example, what happens if you have a constexpr function? Let's say it does something simple, like it computes a square. So obviously you can stick constexpr on it, right? But then the thing about constexpr is kind of it means it can run at compile time, but it doesn't have to, right? That's, for example, something that confused me for a very long time, when it appeared in C++11. And I thought, great, this is like a compile time function. And I couldn't understand for a while that, well, actually, if you give it like a compile time constant like the 3, yes, then it's going to run at compile time. You can use square 3 like as a non-type template parameter or whatever. But if you give it an x, which is a runtime variable, it's going to run at runtime. It's going to be a function at runtime function, which has an address. It is a function. So it is maybe compile time, maybe runtime. You don't really know unless it's obvious. And that's really kind of sometimes confusing and sometimes not what you want. Sometimes you want to say, compiler, this has to be run at compile time. Like, I don't want this ever to run at runtime, right? So this is like, I don't want this to actually end up generating code and slowing down my program. This is something I only want to use for like templates and other things. So please don't generate any code. And if someone tries to use them at runtime, give me an error. And for that, now we have another keyword, which is constivar. So constivar means this function can only be executed at compile time, right? It can never be executed at runtime. So it's not actually really a function. It's not going to have an address. It's not going to like generate any code, or like there's not going to be a symbol of any kind. It's going to be something that can only be used during compile time, right? So now if you do square 3, that's fine. If you do square x, that's an error, because x is a runtime thing. So yeah, so I think the initial syntax for this that was proposed was constexpr exclamation mark, like really constexpr. And then people didn't really like that. There was kind of going back and forth between, what should we do? And then someone at the last minute came up with Constivar, and everyone was like, yes, this looks good. But we still have a problem. So let's say you have some kind of magic function that can compute a square really fast at runtime. Like for example, it uses some kind of compiler intrinsics. Let's say your CPU has like a magic instruction to do like a square really fast. That's not really a thing, but like for the square root, for example, you have an intrinsic. That's maybe a bit more common. So anyway, so you have something that is like a magic kind of compiler intrinsic, which is going to be, that's the optimal way to compute a square. Now, obviously, this is not constexpr because this magic stuff is runtime stuff, right? So you can give it a literal, you can give it a runtime thing. It will always be fast, but it will always be at runtime. Now, if you stick a constexpr on it, well, that's great. So you can use it at compile time now, but at runtime, you can't have your fast magic anymore, right? Because if you stick the magic intrinsic in there, then the compiler is going to say, well, this is not constexpr stuff. You can't do that. So we have a facility now in C++20, which is this thing. Stat is constant evaluated, and that tells you whether at any given moment in time you are currently executing in a compile time, in a constexpr context or not. Right? So what you now can do is you can say, okay, so if I'm running at compile time, I don't care how fast it is at runtime because it's not going to run at runtime. I'm just using it for like a compile time thing. So do the thing that you know how to do at compile time. So this is kind of constexpr, okay, multiply these things together. But if you're running at runtime, then I want to have this magic function. And this is kind of an expert feature, I would say, but I'm mentioning this because I read a blog post like a week ago about someone who didn't quite understand how it works and was confused, and they said, oh, so now this is going to do something else in debug or release, and it's going to be more complicated to debug your code. No. This has nothing to do with debug and release. This is strictly like you use this stuff to say, okay, we have one branch, which is like the runtime branch, which is fast, and we have another branch, which is exactly the same functionality, but in a way that it can actually be compiled at compile time and be like constexpr. So this is the way you use this. And this is typically going to be used somewhere deep in a standard library. For example, to implement something like std square root to make std square root basically constexpr, right? This is what you would do. Like you can compute it by like with polynomials or something, and then you can do that at like in the first branch. And the second branch would call like __ internal square root, which is actually a thing on CPUs. So like this is just like if you see this like while debugging standard library code, now you know what this means. There's one question that usually comes up at this stage. Is anyone okay with this? Does everyone understand how this works? Yes, Chris.
I'm saying I'm okay.
Sorry? You're okay.
Oh, why isn't it if constexpr?
Yes, thank you. So why is it not if constexpr? That's what everyone says. Well, why is it not if constexpr?
Well, because then it would always be constexpr.
Exactly. So if you have an if constexpr, that's a thing that's always going to be done at compile time, which means if you have if constexpr is constant evaluated, it would always be true. So the second branch would never be taken. So that's just doesn't make any sense. So which is why you always stick it in a normal if. All right. So any more questions about this? Yes.
You could write that though, right?
You could write that. You could write. Okay. So again, watch David's talk. So there's these like 2 talks I recommended about this topic. Like the first one, if you watch his talk, he goes on for quite a while about weird things you can do with if like is constant evaluated and weird contexts in which it's like really hard to figure out like what's actually going on. So it's like a nice kind of brain puzzle, but like basically the summary is only use it like this. Right? Whenever you use this, the only way that you should ever use this feature is you have a function body and you say if is constant evaluated, do something else, do something else. No, don't ever use it in any other way, and then you'll be fine, and it's going to do what we just talked about. Everything else is confusing, and yes.
So I imagine you probably wouldn't want to do this, but just that question.
Okay, now we're there. Okay.
I imagine everything inside the body of that is expected that will be a compile time.
So everything that's in the body of the first branch has to be something that compiles in the constexpr context, yes.
Can you put things that won't compile in context?
No.
So it won't allow it.
No. So if you put magic fast square into the first branch, it's going to say no.
Unless you put it behind the branch which was never executed.
Yes. So if you call this whole function inside another function where it's called at runtime from there, then then the second, so then it would be okay, but it would not do the thing you want. It would execute the second branch.
That was going to be my follow-up question. If you redirect to that through another function, would it propagate the context?
Okay.
Context back?
Again, you can. So this is a whole talk, like to figure out how this actually works. But basically, if you look at a CPP reference, like the important thing is where do you come from when you call. So what's like the initial thing, like where you kind of come from in the call stack. And if it's something that you're trying to like figure out what a template parameter is, or you have like a decal type, or you have something that is like a compile time kind of core kind of what's this Sanderd's term for this? Like a beautiful fundamentally core constant expression.
Constant expression.
No, it's not core constant expression. It's like a specific type. It's like manifestly constant expression or something like that. And that it's like a list of things which are those things. Like if you are doing like decal type, if you're inside like a template parameter list and those kinds of things. And if you come from one of those things when you end up here, then you're at compile time.
Like compile time context. It will.
Yes. Yes. So if you basically if you call this from main and you give it a 3, it will take the second branch because you are running a program at that point. Even though, you know, it's a constexpr function, it can evaluate it at compile time, but by the time you're running main, you're already at runtime, and then this thing will be false. So the question is what's the top of the call stack? Is that your program which already runs, or is it something that the compiler is currently doing while it's compiling your code? And depending on that, it's going to be true or false.
So it has to be constexpr all the way back.
It has to be constexpr all the way back. Yes, this is a better way of explaining this manifestly constant expression thing. Yes.
Okay, thanks.
Just wonder, so the first branch is compiled at all or overcompiled?
Well, the first branch will never result in any code, right? Yeah. So if you are, how did you say this? This was a perfect explanation. If you are coming from what?
It has to be turtles all the way down.
Yeah. So if it's constexpr all the way up, like you said it better, but like, okay, if you are currently compiling your program, then you're gonna take the first branch and keep compiling your program. If you are running your program, then basically the compiler so the last thing it will do essentially while it compiles the program, it's going to say, okay, from now on I'm done compiling, so everything from that now on will be runtime, and then it's going to throw away the if and the first branch, and the code you will end up at runtime is just return magic fast square, and that's going to be the compiled body of your function by the time like the thing is finished, compiled, and you actually run it. So this branch will go away.
So effectively, the first branch compiles to an integer literal.
The first branch doesn't compile into anything. The first branch is used during compilation. It's not resulting in any code.
So I think what would happen is if that does resolve to constant evaluate, the compiler would, while compiling it, resolve that first branch into just return some literal, and then like remove the dead code from the second branch.
Yes.
So it just become a function that says return.
Yeah, but then it will not actually become a function because it will return this 3 and it's going to end up in some kind of decal type or template list, and then that's going to be used there, and then poof, it goes away. It never actually results in a function being compiled. So it's like an intermediate result of a compile time computation. Does that make sense?
There's no overhead at runtime, is there?
Sorry?
For skipping the first branch, there's no overhead at runtime.
There is no overhead at runtime. Yeah, at runtime, this will always result in int square, return magic fast square. That's the other thing that this blog post was kind of confused about. This has never any runtime overhead. Okay, this is really important. Okay, yes.
So to clarify, basically evaluate to if false, so the compiler can remove the if false because it's
yes.
Right.
So the compiler knows at compile time whether it's true or false.
Yeah, and if false is...
If it's false, then it's going to remove the branch. So it is, at that point, it is as if it were an if const expr kind of thing for compiler purposes of knowing at compile time it's going to take the other branch. Okay, this is... I wasn't planning to talk about this for that long. It's that kind of topic. We can keep talking about this. There's more very, very interesting cases here, but like, use it like this, you'll be fine. or actually don't use it, but if you see this in standard library code, then don't be surprised, because now you know what it does.
Just an easy question. Do you know if this is available in any compilers now?
I am not, like, we have compiler people here, I think.
Yeah, it's available in GCC 9, definitely. I think Clang 9 as well. I don't think it's in CC yet.
So
Warns on the constexpr thing.
Pardon? Clang warns on the context we're doing.
Yeah.
Oh, nice. GCC doesn't, so.
okay, so the comment was Clang and GCC have it already. MSVC probably doesn't,
Yeah,
and Clang actually warns if you do the typical mistake of writing if constexpr, which is really nice. Okay, so we are almost at the end. I have like a few miscellaneous features left. So one of them is feature test macros. So let's say there's a cool new C++ feature which you want to use, but you can't do that always because you have to support all the compilers. And this is the kind of stuff you had to write before, right? For example, if you're a library and you have to support C++ 98, for example, then you might have a move constructor all the way down in this widget, but the move constructor is not going to work in C++ 98, so you have to kind of if-def it out if your compiler doesn't have basically R-value references, right? But then to figure out whether your compiler has R-value references, you have to do, this is actually like a very short, incomplete version of what you have to do. You have to test for like different versions, and actually if you have to make it work, it's actually longer than this, but this is kind of a simple kind of shortened, incomplete version of what you have to do to figure out whether your compiler has this particular feature. And has you seen this kind of stuff before? Yes. Yes, you've written this kind of stuff. I've also written this kind of stuff. Basically, if you maintain any kind of cross-platform library that supports all the compilers, this is your life. And it's a very sad existence indeed. So from C++ 20 on, we have a better way of doing this. We have, for every feature, we have a feature test macro. So you can just ask the compiler, do you support this feature? So this thing is now standardized. And obviously, if you have an older compiler that doesn't know about these things, then they're not defined, so you're fine. Right? So this will work. Yes, there's a question.
We're saying this is C++ 20 features, so then we're compiling with an old version of C++, that this doesn't exist.
Yes, so the comment was that this is a bad example because this is not a C++ 20 feature, it's a C++ 11 feature. So if you have a C++ 11 compiler, which doesn't know about these macros because it's not a C++ 20 compiler, then this wouldn't work. And yes, you're right, but I expect compiler vendors that they would kind of do the right thing and provide these macros for like any kind of version you want to compile with. I hope so, that people will do that. Please, compiler vendors, do the right thing. Yes?
We have defined this macro up to 98, so compiler vendor are encouraged to do that.
Mm-hmm.
So if you have, at least if you have like a new compiler, but you compile in like C++ 11 mode, right? You have all these macros defined.
Okay, so
basically seems the first standard, basically, so you should be able to do that. But if you have an old compiler, obviously you don't have this feature, right?
Yeah, so the comment was if you have a newer compiler, then even if you are using it with an older standard that you're trying to compile, it's still going to have all these macros defined. Like, you have a problem if you use a really old compiler, not if you use an old standard. Okay, so basically you have these now defined for all language features and also for all library features, which start with like cpp lib. Like for example, here you have cpp lib, three-way comparison. And then we have another thing, you can also now test for whether you have a certain header. Like for example, something I encountered just a couple days ago where I wanted to use span. Span wasn't available. So I took Tristan Bindell's implementation of span, which is awesome. But then I had to like, what if I have a C++ 20 compiler? And then I wrote this. So now you have the standardized has include macro, and you can test for whether you have an include. And if you have it, you include it. Otherwise, you do something else. Except I then ran into a problem. On macOS, where libc++ has this interesting thing where actually if you are on C++ 17 and you include span, the header is there, but it doesn't actually do anything. So so the include will succeed, but if you then use std span later, it will not compile, which is but then then you should actually, like, the right thing to do here is to use the feature test macro and not the include header. And then at that point I noticed, oh, we actually forgot to add a feature test macro for span. So now I'm going to write a defect report to please add the thing. So yeah, somehow we forgot to add a feature test macro for span, because I think span was actually added to CSS20 before feature macros themselves were added to CSS20, and then people kind of didn't remember that. So yeah, this is going to be an NB comment, and we're going to fix this, and when CSS20 ships, it's going to be there. Okay, last thing, or two more things. Do I have time for two more features very quickly? Yeah? There's one question in the back.
So these macros, do they require any header to be included before?
No. The question was, do they require any header to be included before? And the answer is, no, they don't. They're just there.
Are you sure?
No, I'm not sure.
So would be that, what if I have, say, Pleiades pointing to some random GCC standard library? How does it know what features it supports?
There is a new header called version in which all of the macros are defined.
Okay, so probably you need to include version to get them. Sorry, I must have overlooked that. I did not include version when I was using it recently, but maybe it was included in some other system header I was including. Yeah. So yes, that's probably an omission on my part. Yes, you apparently have to include version. Thank you, Corentin. Which probably will be included as soon as you include anything else, I hope.
Basically, yeah.
So actually you don't have to worry about it, but good to know. So if that's literally the first thing you include, then yeah. Actually, is that the reason why it didn't compile? Interesting. Okay, this is more interesting than I thought. Anyway, one more feature using enum. This is from Gaspar Asman. This is really cool. So we have enum class in CSS11, which is great because it's a lot more type safe than CSS98 enums. Problem with enum class is that you have to qualify them with the enum class name if you want to use any of the enumerators, right? So you have to, if it were just a normal enum, you could write case red. Now you have to write case blah, 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 colon, colon red, which is kind of the point. But a lot of people say, well, this is too much boilerplate. This is annoying. I don't want to be writing this. And then they throw this all away and they just use constexpr int instead. In CSS20, you will be able to say, okay, using enum name, and then that's going to bring all the enumerators from this particular enum into your current scope, and then you can use them like this, right? So this is really cool. I think it's going to save a lot of typing. It's going to make more people use enum class, which is the right thing to use. And this is actually really cool because it's actually more powerful than if you use, like, if you say using some function or something. It's more like a using namespace kind of thing, because like an enum is essentially kind of like a namespace with like constexpr ints inside, more or less. So this using enum thing is more or less like a using namespace thing, which means that you can use it at class scope, for example, right? So you can say, if you have an enum class and then you have another class, you can say using enum at class scope, and then those enumerators will be available everywhere in the class. So yeah, that's really cool. And the last thing I have is this. So we have in CSS17 this very unfortunate situation where we have Utf-8 literals, right? So this, of course, it's implementation defined if you can have a file that contains this particular emoji, but if your implementation allows that, this is going to compile. And on CSS17, this is a char pointer, which means that it works, but like if you're, like, for example, if you're on Windows and that doesn't really do Utf-8, then it's going to result in a string that has some gibberish inside. And the other problem is that char star is kind of special because it's this type that can alias any other type, but then you're kind of using it for this. So there's a few problems with this. So in CSS20, we have a new fundamental type. So in CSS20, actually, this is not going to compile anymore because Utf-8 literal is no longer a char star, which is good because that's just doesn't work. So now this is an error, and we have char 8t in C++20, which is a new fundamental built-in type for Utf-8 string literals. So this is now actually going to work even on Windows and actually going to contain a Utf-8 string. That's really cool. And there's library stuff around this as well. So we have now std_u8 string and std_u8 string view as well, which I'm not going to talk about because we're not talking about library stuff here. There's only one problem. There's no IO stream that supports it yet, so you can't actually get this out of your program. But inside your program, you can now kind of reasonably use this. Right. So, by the way, if you have any questions about this specific feature, we have an expert in the room who is not me, this person over here. So if you have any Unicode questions, ask him. Anyway, so that concludes my little overview over small C++20 features. This is just for completeness, all the proposals I have talked about. And yeah, there's a lot of work from a lot of people who put a lot of time into designing all these features and specifying them and putting them in a standard so you can use them. So I hope some of this will be useful, and thank you for listening. All right. Do we have any questions / time for more questions, or?
A couple, if anybody has any questions.
Yeah, one or two.
Yes, Chris.
So constant_init was introduced as a keyword. Why not an attribute?
Why const_init was not introduced as an attribute? Yeah, there was something about that.
So attribute can be ignored, and so anything that has semantic meaning cannot be an attribute.
No,
So basically, the rule is the rule is if you have a valid program which contains an attribute anywhere, and then you remove that attribute, it has to be also a valid program with the same semantic meaning. But what you want for the const_init is if you take it away, actually it means something different.
You want const_init to fail if it's not const_init, so it cannot be an attribute.
So an attribute can constrain what your program is allowed to do, but it can't expand what your program is allowed to do. So you can't ever introduce an attribute that makes something work that doesn't work without it. That's pretty much.
But what about no unique address?
The unique address works whether you actually.
No, because you can observe the behavior.
You can observe it, but both programs are valid whether you interpret the attribute or not.
One of them's wrong.
I think they've played this to the full afterwards. So yeah, that's it. But before everybody runs off, first just thanks again to the speakers.